So hi everyone. Yes, a lot of us are back from lunch now, all well settled. Won the cup also yesterday, right? So
Isala Cup Namdu.
yeah. So yeah, let's get started. So we are here to talk about. So we are from Freshworks. We are here to talk about our internal search platform and the architecture behind all the search in our products, right? And so we'll also cover how we extended the same thing to power the vector-based retrieval also, right? Powering the Gen AI use cases and everything. Right. So I'm Sesha, and this is my colleague Saikumar. We are both part of the search storage team. So this is like Freshworks at a glance. So we would have already heard about this in the multiple talks at the keynote, etc. Right? So Freshworks was founded in 2010, and so we went to an IPO in 2021. So between this period is when we experienced rapid scale, and so like onboarded a lot of customers, launched multiple products, etc. Right? So as you know, Freshworks is a SaaS company, and we have like multiple products, Freshservice, Freshdesk, etc., right? So this architecture which we designed and implemented was done in as a response to actually our increasing scale. So it was conceived and built in 2017, right? So light at the time of our growth phase. So what are the search cases right now in Freshworks, right? So obviously the traditional lexical search. So we offer full text search, and also on the listing page we have the filters and aggregations, right? So that is part of the lexical search. Of course, with the new Gen AI use cases, people asking for recommendations, suggestions for solution articles, etc., we introduced semantic search, right? So this necessitates storing the vector embeddings, providing approximate nearest neighbor search, etc., right? So to give an idea about the scale we are dealing with, right? So as of May 2025, we get about 14 billion write events, and we serve about 3 billion queries. This is done across 25 plus clusters across 5 regions, right? So we are global across 5 regions. So the total number of nodes, all of this encompasses is about, so it's 800 plus nodes, right? Which are part of these different clusters, right? And since this is a search use case, it's like different from the observability and logs use cases. There's not exactly a retention period per se, right? So we have to take care of like disaster recovery. You can't lose data easily, right? So we have the data of some customers are with us since the beginning, right? So like Atwell College from Australia, I believe, right? So those guys are there from the beginning, and their data is still there in our indices, right? So yeah, so all that comes to about 750 terabytes of storage. So when we designed this in 2017, right? So what were the capabilities which the search platform targeted, right? So number one, as I said, it needs to be highly available, right? So we we went into maturity basically, right? From a startup to actually serving more like up the SMB ladder, right? More towards enterprise customers and all that. So these were things which were expected out of the box. So this was a necessary thing. Obviously multi-tenant, so it's a SaaS product, so multiple products, multiple tenants. And so since we were across different regions, like they expanded into Middle East, Dubai, etc., right? So multilingual became a very necessary capability. So multilingual was not something initially we even thought about, but it became a very pressing use case. So obviously all this needs to be cost effective, like we are a business here to make money in profit, right? So, and yeah, so as we'll also cover in the future slides, so technology keeps changing. Like initially we were with Elasticsearch 1.6, right, when we started out. So, but cluster migrations, as you all know, is a very cumbersome process. So we wanted an easy way we can keep ourselves up to date, and easily we can move to the newer features, newer platforms which are available, right? So seamless migrations was also something which we targeted. So this is the high level architecture. So to have like scalability and fault isolation, we try to separate and deal with the things as two separate parts, write path and the read path, right? So in the right part is a typical streaming architecture which we have seen many times before, right? There's the tenant or the product VPC, and it's peered to our search infrastructure VPC. And so that is fronted by something which we call our search service, right? We'll hear about that later. So that search service takes in the events, the right events, puts it into a stream, and so we chose Logstash as our consumer at that time to take care of batching and ingesting all the data into our Elasticsearch clusters, right? So why we chose Logstash at the time was it was very simple in the like a well implemented sync to Elasticsearch at that time, very reliable. It handled all the error codes, response codes which were provided by Elasticsearch, and it also implemented back pressure, right? So what I mean by this back pressure is like if your cluster is going into a state like any index is not able to handle your write throughput, and you get like a high spike in traffic, right? You are able to slow down your consumption from the consumer, right? So this back pressure is being able to be applied, and data just remains in the Kinesis streams. There's just a lag, and we can take our measures or either automated or manual to recover a cluster, then resume your write operations, right? So this back pressure was critical in many cases, like you guys know Flipkart's Big Billion Day sale, Swiggy, you have a search of order. Yesterday we had a search of orders, right? Everyone was typing, hey, match started, chicken popcorn not there, all those tickets came in, right? So all those kinds of huge volume of tickets, you can't always infinitely scale your resources, right? So that's also not a viable solution. So back pressure in the streaming platform is what helps us like smooth out and handle these spikes, right? And apart from this, we also for the sake of more fault tolerance and reducing the blast radius of any issue, we have, like you have multiple topics in Kafka, we have multiple streams in Kinesis, right? So it's use case specific, and it can be like, we have multiple products, right? So product specific. So this control of where we want to route the document, like which stream we want to route it to, that is what is there in the fronting search service. Yeah. So we'll look at that later. Now coming to the read path, right? So the read path is fairly simple. The main job of the search service here is basically, you know, the complex Elasticsearch DSL, right? So we don't want all of our tenants to have to like maintain a copy of the queries which are formed, right? So the search service takes care of firing the queries, retrieving the responses, and giving it back to the app. So yeah, the read path is pretty straightforward. So now coming to an overview of the search service, right? So what were the concerns it was made to deal with, right? The first and foremost thing was tenant lifecycle management. So being a SaaS company, we always have like customer churn, right? Customers come in, they leave, they sign up for a trial, they either upgrade to a higher tier and things like that, right? So all of those events actually affect how we store and save our data, right? So the number of features which are enabled across the tiers, they all change, right? So we either need to move it to a different kind of cluster, different index, or if the customer leaves, you need to delete the data, right? So those kinds of events are fired and managed at the search service layer. Next, so since like you saw in our initial slide, like we have like 25 plus clusters with hundreds of indices across, right? And like Sridhar was mentioning in a keynote, our founder's idea was to serve the long tail of the Fortune 5 million, right? So there are like more than like 1 million tenants which are actually live, right? So all of these tenants across all of these indices, it was cumbersome to just manage using the Elasticsearch routing layer. So we moved the sharding and routing to the application layer. So that is another concern which we offloaded to this search service, right? And of course, like I said before, the query templates, right? Templatizing this Elasticsearch DSL query and having multiple like multilingual copies of it, this was also delegated to the search service. Plus, of course, for our experimentation, A/B testing, feature like canary deployments and all that, we have the feature flags, right? So this is also part of the search service. So you see like there's like multiple levels of configurability here, right? So all this configurability without any kinds of insight or observability into the system will lead to disaster, right? So that's why each of these options and everything, you have the audit trails, the metrics exported to our observability platform, everything is there. So you will know specifically for a tenant what is the current state it is running in, and if you want to look up like 2 weeks back what was its state, or which tenants were live in what index, etc. All of the audit trails and observability is baked in here. So this is a simplistic schema of like how we handle the metadata, right? This is a simplified version for explaining I put here, right? So at that time, if you guys remember, like 2017, 2018, it was all like NoSQL movement, right? All MongoDB, DynamoDB, all of this we go with. But for us, right, so we prioritize like consistency and data integrity, right? At no point we wanted any corruption in our data, right? So that's why we went with MySQL and decided on a relational schema. Funnily enough, now like SQL is cool again now, right? Like, do you guys know all these vibe coders, which is the most favored database which they choose? Any ideas? Yeah, Postgres. So they all like Postgres now. So SQL is cool again. So, but at 2017, 2018, that was not the case. Everybody was like NoSQL, DocumentDB, MongoDB, and all that, right? So if you see the schema, right, it was made to address two major questions. You see the account routes table and the account templates table. So account routes table, it answers the question of, for this write event or a read event, which cluster and which index should I route it to, right? It's a mapping between a product account, a document, which is basically a use case, and a route. A route is nothing but an index and a cluster, right? So this combination is what was very flexible, and if you wanted to isolate, for example, like PhonePe has a lot of UPI failures, there's a million tickets coming in or something like that, you can easily isolate into even a separate cluster, a separate index. All this is real time, by the way, right? So you can hot reload this. So you can easily reload all of this and make the adjustments as and when you need, right? And same for the account templates too. For example, people are trying out, like a new customer is coming in, they have a different kind of use case itself. You need a different query over there, right? The product teams are like, they can feel free to upload their specific templates in there, and you can have this customization of a specific template just for this account, just in this region, right? So this level of flexibility is what having the metadata outside of Elasticsearch allowed us to have. So yeah, now I'll hand over to Saikumar to talk about how our Elasticsearch cluster setup actually is and how we did the migrations using this service.
Thank you, Sesha, for neat walkthrough of the SES service design and its capabilities. Now let's talk about the ES setup which I had 2 years ago. Yeah, self-host clusters. We run self-managed ES clusters on AWS, and basically we used to run ES6 and Java 8 for the older clusters, and we use the master data client setup, which ensures the higher scalability and improved performance during the high load scenarios. And so let's come to multi-zone deployment on AWS. So we operate in the, as Sesha said, in the 5 regions on the AWS, and our clusters deployed across the multiple availability zones in the each region. And we automated the deployment process by using the Chef space and AWS System Manager. With one click from the AWS console, you can spin up any node to any cluster at our side. And zone-based awareness. As we mentioned, right, and everyone knows about the shards and replicas, right? We use the one primary and 2 replica configuration for all our clusters, and we used the Elasticsearch zone-based property to spread shards across multiple availability zones within the region. And with this, we ensure that our primary and its replicas never end up in the same zone. Even when zone goes down, we can still continue to read and write without interruption by ensuring the high availability. Subclustering. This is logically separating the bigger indices and smaller indices. One challenge we faced was by handling the indices of various sizes. We implemented a subcluster concept where we can have the dedicated set of nodes for the bigger indices and another set for smaller indices, which improves the query performance and resource isolation and cost optimization as well. Snapshots and DR readiness. So we enable the data backup through ES snapshots, and we will be taking the daily snapshots through cron job and will be pushed to S3. And we can restore the data for any indices from snapshot whenever we require or whenever we see data loss. Basically, as a SaaS company, we need to have proper planning for DR to protect customers' data and maintain uptime. So coming to challenges is Elasticsearch. Even though we have built highly available and scalable system using Elasticsearch, there are few challenges we have encountered over the time. As you see, increase in latency, performance issues, and cost increase for the infrastructure as the data and scale grow over the period. And as you mentioned, right, there is operational overhead for the managing the old age infrastructure. And as you see, if you want to use new features after Elasticsearch version 7.10, right, we are not able to use it because of the ES closed license, and which made ES as not an open source solution anymore. So basically we always prefer to use open source solutions at our systems. So then we checked the alternatives for the Elasticsearch, and we found the OpenSearch was the best fit solution for the Elasticsearch, which offers the same capabilities, and it is direct fork of the Elasticsearch 7.10, and it makes it compatible with our existing setup. And during our evaluation, we wanted to go with the latest stable version of the OpenSearch, which was 2.3.0, as take the advantage of the new features and improvement. And backend, we also analyzed the breaking changes between Elasticsearch 6 and 7 and OpenSearch 2.3 and 1.3. And this also helps us identifying the changes in the indexing behavior and query and API compatibility. And next, we also ran the benchmarking on between Elasticsearch and OpenSearch. For this benchmarking, we have used the Elasticsearch version 6.6 and JDK, which was running on our clusters at that time, and we took the latest version of the OpenSearch, which was 2.3.3 and JDK 17. And hardware configuration is we used for the single node cluster on 4 CPUs and 32 GB RAM, and we took the sample of the 500,000 tickets data. Basically, we want to test the indexing performance and query latency. These are the two key parameters we keep on changing based on the increased load. So indexing performance, which is improved by 300%, and query latency dropped by 70%, which gave the confidence to choose OpenSearch as a rightful solution to replace Elasticsearch at our end. So migrating from Elasticsearch to OpenSearch, you can consider this is like a blue-green deployment. So basically, we have provisioned the OpenSearch cluster with version 2.3.0 along with Java 17. We have created all the required indices, and with the mapping changes respect to OpenSearch. As you see here, right, we have as Sesha mentioned, we have a set service where we can have the dual write concept. So basically, updating the secondary indices at dual write side, it can expose the event parallelly writing to both the clusters at a time by syncing the data in real time. And we have and so as we compare, right, so we have covered the only live part. So we need to backfill the old data from the Elasticsearch to OpenSearch. For that, we have used the log/stash pipeline and performed the reindexing from Elasticsearch OpenSearch by index. With this, we cover the historical data and live data between the Elasticsearch and OpenSearch. And coming to testing the read consistency between Elasticsearch and OpenSearch. So as you see, right, as Sesha mentioned, and we have a query templates to check each query coming to the storage cluster, which is Elasticsearch or OpenSearch. Based on the query template only, we need to get the data from the data store. So We have rewritten the query templates with respect to OpenSearch based on the breaking change which we found between Elasticsearch and OpenSearch to have a alignment with the current search behavior. And as you see, right, there is a framework called GitHub Scientist. We use the GitHub Scientist to mirror the reloads between both the clusters and comparing the search results in the real time without affecting the live traffic responses. Now coming to topic C. So once we are happy with the results accuracy between Elasticsearch with OpenSearch, so we stopped writing to Elasticsearch and enable the live reads from the OpenSearch by using the search service feature toggle at our end. So after later on, we have cut down the writing to Elasticsearch cluster, and we have cleaned up the old Elasticsearch indices and infra as well. After this migration, right, we got benefits by using the OpenSearch. So 50% reduction in the latency, and we stopped at the 60 plus nodes after migration, which helps in the 20% cost savings on infrastructure per month. And we are able to use new features called hybrid search and searchable snapshot. So Sesha will explain how we can integrate hybrid search with OpenSearch by choosing the vector data source. Handing over to Sesha.
Thank you, Saikumar. So so now we enter the semantic search and the Gen AI use cases, right? So like everyone, we also followed the hype, of course, looked into the expanding ecosystem of all the vector databases which came in, right? It was Pinecone, Milvus, Quadrant, each company and everyone, there were so many Rails frameworks and Ruby gems back in the day. Now there was a vector DB for everyone, right? So before that, we came up with a list for ourselves, right? So what is the criteria that our vector DB have to meet, right? First, of course, we are big lovers of open source. We want to be able to interact, contribute, and influence the roadmap, right? So we want it to be open source. Of course, we need support for multi-tenancy, and so we also need fast vector search, but we can't compromise on good precision and recall, right? So that was another criteria which we were hard on. Right? And support for hybrid search will be good, because since the initial days we never believed just vector similarity can address any of the use cases, right? So we still believed in information retrieval as a whole thing, right? And of course, like I said before, an active support community, so that we are all going to walk on the cutting edge. Better to go with someone, right? So these were the criteria which we looked out for. And before that, so we actually looked into some of the use case of vector similarity which internal teams were doing, right? Turns out people were already doing cosine similarity using the script and the painless script scores, right? On the existing clusters, right? So what is the big difference? Is there something new which is being done here? So one is the transformer based embedding models, right? The dense vectors were increasing in number of vector dimensions from word to fast text and all that, right? So the scale of the problem is what is changing over here, right? And with more adoption of vector based use cases, earlier people were doing vector similarity across say 100K documents or something. Now that was going into millions, right? Because of conversational use cases and lot of the RAG use cases, etc., right? So to give a bigger perspective on how much I mean in scalability, right? So this is some tentative numbers. For example, if you just have 1K or 10K use cases documents or vectors to do a similarity across, you can just use the KNN itself, right? Just cosine similarity, you don't need to burn yourself. You will get results in the order of milliseconds, right? But approach our typical tenant scale, tens of or hundreds of millions, right? You go into the order of minutes, right, for the exhaustive KNN search. So this is what necessitated an approximate nearest neighbor search, right? So, but yeah, we have saved. OpenSearch itself has a KNN plugin, right? So we went and looked into that. So the KNN plugin gave us multiple options, right? There were multiple engines, the NMSlib, FICE, and the Lucene engine itself, right? So these engines majorly implemented two similarity algorithms, which were HNSW and IVF, right? So we did a comparison across these, and one major consideration which we had during our comparison is, so we, as you guys know, are a multi-tenant company, right? So some of these use cases do not support filtering while you do a vector similarity, right? Some of these engines, they don't support that. So what that means is you have to have an index per tenant, right? So like I said, long tail, 5 million customers and all that, so you can't have 5 million indices again, right? So we try to follow the approach we already used, which are lexical search, right? Same application layer sharding, try to bucket multiple tenants into a few indices, like across a few indices, right? So, but when you do that, with every vector similarity search, you would have to have a filter criteria of the account ID, right? So, without affecting our precision and recall, like the Lucene engine with HNSW was the one which was acceptable for us, right? Because it implemented filter with, like, while the search was being performed, right? Kind of like a filterable HNSW. The other DB which I saw in the market which is doing that is Quadrant. So they have a filterable HNSW, and which is why it's being used at Twitter. Okay, yeah. So moving on, this gives a high level overview of how our current hybrid search architecture, which is in POC, is, right? So streaming architecture typically for the ingestion, right? You go via Kafka topic, there's an async worker which hits an embedding service. This embedding service is hosted on Python Ray cluster, right? If you've heard of Ray, you might be familiar. It's a Ray cluster, right? So that's on GPUs, and then so once the embeddings are produced, it's the traditional way. You just index into our via our search service. You can take decisions of where to route this, which index to route it to. So the vector along with the document, in our cases mostly it's chunks of documents, right? So that's indexed into OpenSearch. So for the sake of easy experimentation and because of how the teams are also organized, right? So we are the search storage team. There are separate like data teams, search relevance teams, etc., right? So because of that, we decided to keep the hybrid search outside of OpenSearch. So we didn't use the inbuilt capability which OpenSearch provides, right? So how that works is they fire the queries in parallel to the lexical part and the hybrid part, right? And the vector similarity part, and they do their own re-ranking like either Cohere or something like that, and then you get the hybrid search and the results to the user, right? So yeah, so when you adopt new technologies, obviously there are going to be problems, right? So one of the biggest problems we faced, and we were also talking with a few people yesterday about that, was like Elasticsearch and OpenSearch all have this primary and replica model, right? You have this replication which is happening. The traditional document-based replication, it means that indexing happens on both the primary and the replicas independently, right? There is no correlation at all. But because of the nature of the HNSW algorithm, right, they have a random seed which is initialized for each batch of documents. So depending on your batch size or the number of documents which come in, right, the graph construction can vary, right? So that's what we actually saw happening in a few cases. The graph construction between the primary and the replica would differ, and there will be like subtle differences in the ordering of results when it comes, depending on whether it hit the primary shard or the replica shard, right? So this was a problem for us. So one obvious solution to this is the segment replication feature, which has been rolled out, right? And it's also there, and it's going to be improved in OpenSearch 3. So segment replication means that there is no multiple indexing and all that. Whatever segments are built and whatever data structures are built in your primary, they're just copied over the network onto the replicas, right? So it'll all be consistent. And the only downside over there is, one, there can be like segment replication lag, and two, like the network transfer cost, right? AWS loves to milk us on that. So yeah, so that is a big thing. And the next thing is, of course, HNSW is a very memory intensive algorithm, right? So billions and millions of vectors. Everybody, all data scientists like to use the best embedding which is out there, right? 2048 dimensions and all that. So that quickly adds up to costs, right? So we don't want to bankrupt the company before we just try out the use cases which we can figure out, right? So this needs like quantization and all that from our side, right? So the Lucene engine which we chose, it mostly supports scalar quantization. So vectors are ingested as FP16 floats, right? So scalar quantization gave us some performance benefit, but so it was still not enough for us, right? So that's why we are really excited about the new feature of disk-based vector search. So what that does is, in memory for your fast search and all that, right? It stores a binary quantized vector representation, right, in the graphs and all that. But on disk, you still have the full vector representation. So due to the combination of this, they claim to not affect the precision on recall, even if you do a binary quantization, right? So we are excited to try that out next. That's in the pipeline, right? And with all of these changes which we keep doing, right, changing the vector similarity algorithm, some people want cosine similarity, or they want to change that Euclidean distance, anything like that, right? On their side, the data scientists and the like search relevance guys, they will measure on their data set, right? They'll measure based on the NDCG scores and all that. But from our side as a search storage team, how do we make sure when we change an underlying implementation, how do we make sure we are not negatively impacting anything, right? So for that we came up with something or we borrowed from open source something called the continuous recall measurement. So engines like Turbo Puffer and Pinecone already do that and offer that. So continuous recall measure, what that is basically your production querying is going to be sampled, right? We do like 1% sampling, and what do we compare against, right? We don't have like truth data and all that, right, over here. What we compare against is the KNN or exact neighbor search of the same query, right? So that is going to give you the full precision and recall, right? Because it's just a vector comparison between all of them. There is no approximation over there, right? So we compare between the ANN and KNN over there for 1% of the queries, live production. And based on that, we push out metrics and keep watching them, right? So what enables this is again our routing feature in our schema, right? And what Saikumar was mentioning, there's the framework called GitHub Scientist, right? So that makes sure like any of these jobs are asynchronously executed and it doesn't affect any performance in the live path, right? Yeah. Lastly, of course, we keep experimenting and trying out new like use cases. What more can we power in our company? And so memory is a huge thing right now, right? Agentic memory, and you need to remember the actions it's previously taken. And again, being multi-tenant, it's going to be across conversations, right? So one thing we are also trying out is an integration with Mem0, right? So it gives a nice summary of key facts from your conversation, and like all of you guys would have used ChatGPT, right? It remembers your stuff in that conversation. You open a new conversation, it's something else, right? So that kind of capability is easily given out to us by Mem0. You don't have to each time put in the entire context of the previous chat history into the prompts. You can just use Mem0 to extract the key information, store it, later retrieve it and put it in, right? So we open sourced and contributed an OpenSearch connector for Mem0, right? So that is also being trialed out right now. Yeah, to give an idea of the scale, which we use our in-house observability platform. So this is we hit about 320 to 300 to 320 writes per minute. 320K, writes per minute. And so the ratio of reads and writes is, because it's a search system, it's not like a logs or something, it's not very far off, almost like 1:3. So we hit about like 100K, 110K reads per minute. Yeah. So all of this is served at an average latency of about 100 to 150 milliseconds. Yeah. Yep. So this gives an overview of the search implementation and how we extended the vector-based implementation, right, at Freshworks. And yeah, thank you. Thank you so much. Any questions?
So you went with Lucene HNSW, right?
Yes.
So one of the limitations that OpenSearch only tells is it can support up to 10 million or something.
Yes.
Right, whereas face and all can scale up to millions of vectors.
Yes.
So have you had that issue in yours, or did you handle it any different way, or is that not a issue that affects you guys?
Yes. So what the subtle difference there they failed to mention is with the filtering part, right? So your filtered set, if it's in the 10 to 100 million range, it's still fine, right? But in the other cases, they either do a post or a pre-filter only, right? So that's where they compare on the entire data set which is stored. So for us, like we are able to give an average performance of 100 to 150 milliseconds. That's working out fine. Yeah. So now the FICE engine is also implemented a filterable HNSW actually. Yeah. So we will be trying that out. Yeah. Excuse me. Yeah. Right.
So with respect to the scale and performance, which numbers you mentioned, right? So 320K documents per second, something like that. So what is your cluster size in that? So that should be the important factor, so which will account that. And another one is like when you talked about KNN and then ANN, something like 1K, 2K, 1 million.
Yes.
So is that like dimensions of the vector or the number of the documents? So that is also have clarification.
So for the second part, that list is the number of vectors which are being scanned as part of the query, 1K vectors. So similarity of a vector versus 1K vectors. If the set has 10K vectors, what would be the latency for comparison?
Okay.
Like
so
that.
basically you compared and then
Yes. Yeah.
Using
so
cosine
what
similar.
is changing is because earlier it's also people were doing this script score based vector similarity, right? And they were fine with it. The data scientists mostly they were doing it as an async process, right? As part of their training and all that, right? So 100K vector comparisons and all they were able to do and they were fine with the latency. But now we need it in a real time fashion, right? So that is why we need the ANN and we need to sacrifice on a bit of this precision and recall over here. And for the cluster size part, Saikumar?
And same,
Yeah.
so the resources for this, right, when you publish something like 1K, this is the latency something, right?
Yeah.
So what are the resources used, so GPUs or hard?
Yeah, this was on the CPU and so our one node comparison on SSDs. So i4 X large was what we did, yeah. Saikumar on cluster size?
So basically we have two kind of clusters currently which serves the search use cases, another one serves the vector use case, right? Currently we haven't seen that much increase in the vector usage. So currently we are using i3 4X large which comes with the 128 GB RAM and 16 CPUs, I think so. So we have separated the search workloads and vector workloads. We have dedicated.
How many nodes?
Currently we have around 6+ nodes to handle the around 10 million vectors, means 10 million documents.
Hi, so I was looking at your benchmark results that you published, and you compared between Elastic 6.6.2 and OpenSearch 2.3, right?
Yes.
So I'm just curious, did you compare against the original version from which was forked? Because 6.6 and 7, Elasticsearch 7 is a lot of difference, and OpenSearch was forked from 7.10. So even the Java version from 8 to 17, there's a significant difference.
Yes.
So have you done the benchmark with actually apples to apples? And the second question is, again, you can choose to answer at the same time or later. The other one was, you're calling it a single node cluster. So won't your query latency actually also reflect the bottleneck that it would be encountering?
Yeah. So what we wanted to know was the throughput of a single node in this case, right? So that's why we did the comparison with just a single node. Of course, like it was a cluster, but what we really wanted to say was like there were client nodes and master nodes and all that, but it was served by the data on a specific shard, which means based on our routing, all the accounts, like the 500,000 documents of a single account, right, they were served by one shard, right? So which was typical in our case for the routing, right? So that's what we wanted to exactly compare. And yeah, like you said, most of the optimizations I would not say is all because of switching to like OpenSearch, right? The JDK played a part in it. And of course, they made a big change from 6.6 to 7 in Elasticsearch itself, right? But this is the recorded benefit that we got. Yeah.
Thanks.
The main change, we wanted to use vector based, right? We want to support the vector related loads by using the OpenSearch. So even if you want to use for Elasticsearch, that is licensed, right? We don't have a other alternatives for the by replacing the Elastic to choose the vector workloads. For that, we chose the OpenSearch, and that time only latest version is 2.3.0. So we tested with the that version.
Sure. Thanks.
Yeah.
Any other questions?
Great.
Yeah.
Thank you so much, guys.
Thanks, Sesha and Sai, for an informative session. Thank you.
Thank you.